All right, y'all. So I am going to go through the unit review. Um, and I may have to pause this video a couple times. My kiddo is stuck in Gatlinburg, so I'm waiting on him to call and just things of that nature. But I will do my best to get through it as quickly as possible. But nonetheless, we're going to go through each problem. And then I will also do an additional review video of a second review if we are still not back in school uh, Tuesday. So we will see what tomorrow brings. All right. So the entire unit test review for Unit 1 is on 1.11 all the way through what we did the other day. So the entire Unit 1. So we already had the test on 1A. So this is the entire Unit 1A and 1B test. So it's cumulative. All right. Number 1 says determine the domain of the function. Write your answer in interval notation. Okay, so remember when we're talking about domain, we're talking about x values. Okay, well, the first thing I'm going to want to do is factor both the top and the bottom. All right, so I'm going to do that. I'm going to work that out for you. 2 times negative 15 is negative 30. So that's going to be 6 and negative 5. But those have to be divided by 2. So that's going to give me 2x minus 5 and x plus 3. The denominator would be negative 21 and negative 4, so negative 7 and positive 3. Okay, so a couple of things I do know here. I do know I have a whole at negative 3. So the whole at negative 3 is an x value of negative 3, which means it's going to impact my domain. And then I would also have a vertical asymptote over here at 7. So that's going to be the other thing that impacts my domain. So those are two values. We've got x can't equal negative 3 because that's going to be a whole. And x can't equal positive 7 because that's going to be a vertical asymptote. So then my domain is going to be from negative infinity up to negative 3, union negative 3 to 7, union 7 to infinity. And of course, as soon as I start, my dog rings the bell that she needs to go out. So I might have to stop and do that as well. All right. Number 2. All right. Write a polynomial function g of x that would have the following end behavior. So you're going to see on the answer key here, your answers can vary. Okay. But we're looking at 2 main points here. You're going to notice that the ends are going in opposite directions. Okay. Which tells us that we're going to be an odd degree. Okay. And then negative infinity is going to positive infinity, and positive infinity is going to negative infinity. So here's the 2 things we need. All right, we have to have a negative leading coefficient, and we need to be an odd degree. And again, you can have anything you want. I have just a simple one here. So I just wrote g of x is going to equal negative 2x cubed. All right, so one thing I did do before I started recording is I pulled up Desmos and typed in, I think, everything that was calculator active already. So when I go to question number 3 here, it says utilize the graphing utility. So I am going to go ahead and go to my Desmos and show you, but we're looking for our relative extrema, which we know are our x's, our mins and max, sorry. Okay. And we will also find our absolutes as well. Relative includes both. So I have already done that. So let me go here. And okay, so that's the first function that's typed in up here. So if I click off of these, so you will see we do have an absolute min down here. Then we have a relative min and a relative max. So we have a relative min over there at x equals negative 2. Which is the ordered pair negative 2, 0. I'll go back to my page in a second. We have a relative max right there at, so this was our relative min. so relative max, at x equals negative 0.84307, which is the ordered pair negative 0.843 and 2.080. All right, and then let's talk down here about the absolute. So this is an absolute min. Okay, so remember when we write our absolute min, you want to say the value of it and then the x value. So our absolute min is at negative 1.623. Okay, so our absolute min of negative 1.623 at 0.593. So the min value is important there. So let me go back to my page and show you what I'm saying. Okay, so when I write that, my absolute min of negative 1.623 at x equals 0.593. So that's what you're looking for in that problem. All right, so moving over to number 4. It's asking about any holes, asymptotes, x-intercepts of the function. All right, so obviously we know we've got to factor first. I'm going to fully factor here, pulling out my x, and then I would factor using my x box with x plus 6 and x minus 4. Factor out my 3x, and that's going to give me x minus 4. All right, so let's talk first about the hole. So we see immediately that we've got a cancellation with x minus 4. So we have a hole at 4 something. Okay, you also have a cancellation right here with this x. So we have another hole at 0. All right, so now you can kind of see my reduced equation right here. It's going to be x plus 6 over 3. So if I plug in my 4, 4 plus 6 is 10. 10 over 3 is going to be this value. And if I plug in if I plug in 0, then I would get 6 over 3, which is going to be 2. All right, vertical asymptote. So once you simplified the bottom, there was no x's left in the bottom, so we do not have a vertical asymptote. Remember, horizontal asymptote, again, is Bobo-Botten. So bigger on top is Botten, so that is none as well. All right, we do have a slant because we are exactly 1 degree larger on the top than the bottom. Okay, so we do have a slant. And just for that, the reference here would be that slant asymptote is y equals 1/3 x plus 2. So holes, asymptotes, and x-intercept. So the x-intercept is where the top is equal to 0. So that's only going to happen at negative 6, 0. So there is everything we need to know there. All right. All right. So moving on to number 5. Okay, so this goes back to Desmos. All right, so I'm going to talk, I've already put it in there. All right, and it says what happens to the concentration of the drug as T increases. Okay, so we can look at in behavior here. So we're going to go T increases, obviously. We're going to positive infinity. But we can also talk about this analytically. If you look here, if T gets really, really big, the bigger the denominator of a number comes, then it gets closer and closer to a certain value. And we know what that value is. And you'll see that on our in behavior. So should have just left it up here. All right, so I'm done with this one. Let's turn this one on. Okay, so here we go. So if I zoom out, you're going to notice as T increases, gets closer and closer to 0. And we would know that, obviously, because we can do Bobo-Botten in this situation. Bobo bigger on bottom would be 0. Okay, so we know as T increases, the concentration of the drug approaches zero. And I mean, that's just, kind of common sense in this situation. When you take medication, anything of that nature, the longer the time passes, the less of that is in your system. All right, what is the average rate of change between the hours of 10 and 20? Okay, so I'm going to write out our formula because we just need to remember to practice that. So AROC is going to be C of 20 minus C of 10 divided by 20 minus 10. Now, since I have already got that function in Desmos, I can go over here and let's see if I can calculate that. Let me do this real quick. Okay, so all right, so if I want to do C of 20 minus C of 10, and you could also just do these individually and write them out, over 20 minus 10. And there we have negative 0.198 would be our value there. And we're dealing with milligrams. C is in milligrams per liter. And then over time, it's going to be per hour for us. All right, what would a reasonable domain be? Obviously, our time here cannot be negative, so we know that t has to be greater than or equal to 0. And then use your calculator to determine the time at which the concentration is the highest. Okay, so highest right here, we're looking for the max. All right, so all of that wording is very imperative for your AP exam as well. Let's go back here. Turn this back on and let's look for our max up here, and it automatically tells me our max. It happens at time of 5. The max is 6, but it says you just kind of determine the time. So T equals 5 hours after injection. Okay. All right, moving along. Number 6. All right, so we've got a graph here, and it's going to ask us about transformations of this graph. All right, so we know several things are happening here. All right, several things are happening here, and then we are going to graph that. So a few things that are happening. First thing I'm going to notice is that we are inside right here. So that is going to be a horizontal translation right 1. All right. I'm going to reflect over the x-axis. I've also got a vertical dilation by 2. And I have a vertical translation up 5. All right, now all 3 of these affect our, like reflecting over the x, vertical dilation and vertical shift affect our y's. And this is going to affect our x. So if the only thing affecting our x, we're going to write our equation out. The only thing affecting our x is right 1. Okay, then we're going to need to add 1 to our x values. That will move it to the right 1. And then we're going to do all 3 of these. So we're going to flip it over the x-axis. We're going to dilate it by 2. And then we're going to shift it up 5. So that is our translation equation. All right, and then I did go through here and I just wrote out, you could do this individually, like you could literally just plug in -3 as your x and add 1 to it and plot that point. So I did over here, I actually wrote out my ordered pairs. Okay, and then I wrote what they are going to translate into if I plug them in. So in other words, if I did -3, -1, 0, and 1, and I added 1 to those, it's going to give me -2, 0, 1, and 2. and still adding 1 over here, it's going to give me 3, 4, and 5. And then for our y value, you would take the number. So I would take 2, multiply it by 2, which gives me -4 there, plus 1, plus 5 would give me 1. And I would do that for each one. So I would plug in 2, same thing. It's going to give me 1. I would plug in 1, and so forth. So I'm just going to write those out. 3, 5, 7, 5, 3. And then I'm just going to plot those points. So -2, +1, 0, 1, 1, 3, 2, 5, 3. I don't have 7, so I'm just going to go up here and make what a 7 would be about. 4, 5, and 5, 3. Okay, and here we are. So if you notice, we did reflect. We are taller, okay, which is vertical. We're good to go. All right, the functions P and Q are defined for all real numbers in the xy plane. The graph of Q is constructed by applying 3 transformations to the graph of P in this order. A reflection across the y-axis, a horizontal dilation by a factor of 3, a horizontal translation of 8, and a vertical translation of -2. Okay, so we got a reflection across the y-axis, horizontal dilation by a factor of 3, horizontal translation of 8, and a vertical translation of -2. Now, I understand that seems like that's 4 and it said 3. However, the reflection can be added to your dilation in general, so that could be taken care of in one step. All right, so let's talk about what this is going to give me. Q of x equals, all right, reflection across the y-axis. So x-axis is an outside negative, y-axis is going to be an inside negative. Okay, so understand we're dealing with just f of x, like we're starting with, I guess it's p of x technically. Okay, the graph of Q is constructed by applying transformations to P. Okay, so if I start with P, I think on my key it does say F, but P is what the problem says. All right, so if I start with P, if I'm doing a horizontal dilation by a factor of 3, that means inside, which means it's 1 over B. Okay, so that's going to be -1/3. So the negative is my reflection, the 1/3 is my dilation. All right, X translation of 8, so that's a +8, so I'm going to put a -8 here. And then we are going to shift that vertically down 2. So there is your answer. Okay, and I just wanted to make a little note over here that had it said a vertical dilation by a factor of 3, then you would have the 3 out front, like so. Okay, it wouldn't be inside of the function. All right, so just be mindful of that. All right, that's why I left a little blank there, but I don't want to write it in there. All right, number 8, the graph of P of x is shown. Calculate the rate of change from -4 to 1. So we're going to start with that. That just means P of 1 minus P of -4 over 1 minus -4. So P of 1 is going to give me -1 minus P of -4 is going to give me -3 divided by 5. It's going to give me 2/5. Okay. All right, and then we're going to do the same thing for 5 and -2. So P of 5 minus P of -2 divided by 5 minus -2. All right, P of 5 is going to give me the value of 3. P of -2 is going to give me -1. I'm sorry, P of -2. Oh, no, -1's my whole. So 3 over 7, which would just give me 0 over anything is going to be 0. All right. All right, find the missing value of g of 6 over this interval. Okay, so what we're trying to do here is figure out a pattern. Okay, so if I start looking, what's happening here, we are adding 6.5. And then here we are adding 5.5. And we're adding 4.5, and we're adding 3.5, and we're adding 2.5. So then the next one would be to add 1.5. So our answer would be 26.5 plus 1.5, which is going to give me a value of 28. All right. Number 10. Write a rational function r of x. All right, write a rational function r of x that has a hole at x equals -5, vertical asymptote at 7, and a horizontal asymptote at 3/4. All right. So let's see. We've got a hole at -5. That means we are going to have. So we're talking about r of x, right? Okay. Hole at -5 means we're going to have an x plus 5 on the top and the bottom. Vertical asymptote at 7 means I'm also going to have x minus 7 as the denominator, and a horizontal asymptote at 3/4. So you do need a 3 and a 4. Now, here's the situation here. All right, so this is all this tells me is I have a hole at -5, I have a vertical asymptote at 7, and it tells me I have a horizontal asymptote. So one thing you know right here is our exponents are the same, okay, for us to have a horizontal asymptote. Well, the problem is that I don't have, right now I've got a power of x to the first, and down here I would have x squared. So I need another x. I simply went in here and added an x. You could put it in front. So like you could really come right here and put it right here. So it'd be 3x and x plus 5. Like so. That way, if you distributed that out, you would have an x squared on the numerator. You could also have multiple things that went there. This is just the easiest way to make that happen. Obviously, that would mean that there's other things that are happening on this graph that are not listed, but in order to have that horizontal asymptote, I do have to have that power being the same, okay? All right, number 11, let's factor the top. Okay, I see nothing here is going to cancel. I have a vertical asymptote then at x equals 3 and x equals -2. I have a horizontal asymptote at bigger on bottom. Bobo is 0. I have x-intercepts. I have an x-intercept where the top equals 0, so that's going to be at 2, 0. And I have a y-intercept at 0, -2. So I'll plug in 0 for everything. So that's going to give me -4, -3, and +2 would give me -6. So -4 over -6 is going to be 2/3. So 0 and 2/3. All right, so let's talk about what we've got on the graph so far. We've got a horizontal asymptote here at 0. We've got a vertical asymptote at 3. And at -2. All right, we've got a 0 at 2. And we've got a y-intercept at roughly 2/3, so somewhere around in there. Okay, so you're going to follow your asymptotes as best you can. We can do sign analysis here to decide which one it is. So like, it should follow your asymptotes. So it should look like this. Again, we could do sign analysis to see this. So you could pick a really, really big positive number and go there. So that would give me the limit as x approaches negative infinity. It would equal 0. And that's just our end behavior, not our limits necessarily. So we're just talking about on our two ends. Okay. All right, solve the inequality. So remember, first thing we want to do is set our inequality equal to 0. We're going to factor by grouping here. So that gives me x squared minus 9 and x plus 5. And then x squared minus 9 will go again. Okay, so then over here on my sign analysis, I have -5, -3, and +3. Those are my 3 zeros. Okay, none of them are happening more than once. So we're good there. And then sign analysis, if you pick a really, really big, either way, okay, odd dots are going to change. So everything's going to change and you should end up with that sign analysis right there. So if it's asking for when it is greater than 0, you're looking for this area and this area. So that's going to be from -5 to -3, union 3 to infinity. It did not say equal to, so we use parentheses, not brackets. All right, so now let's look at number 13. All right, let's talk about what needs to be put on our sign analysis. It's already factored, so that helps. So we've got +5, we've got -2, we've got -1, and +3. So -2, -1, 3, and 5. None of those happen more than once. -1 and 3 are our asymptotes, so they don't have a value. -2 and 5 are our zeros, so they're going to be solid. All right, and again, odd dots are all, everything's going to change here. If you pick a really, really big positive number, I know I'm going to be positive. That will make everything positive. So I'm going to be positive, negative, positive, negative, positive, or you could start negative. Nonetheless, you would divide two negatives, making a positive. And we're going to go from there. We want to be less than or equal to 0. So we're looking at our negatives. Okay, so since it's less than or equal to, we are equal to at -2 up to -1. We're not equal at -1. Union, we start again at 3. We're not equal to at 3, but we are equal at 5. Most missed part on these type of questions is your notation. So make sure you got brackets where you're supposed to have brackets, parentheses where you're supposed to have parentheses. Okay? All right. Number 14. All right, determine whether the function is even, odd, or neither using your algebraic test. Okay, so remember the algebraic test is we're going to plug in -x into the function. So we're going to do f of -x, which means I'm going to do -x quantity cubed minus 7 times -x quantity squared plus 12 times -x. And I'm going to simplify that out. If you cube a negative, it's going to stay negative. If you square a negative, it's going to become positive. So that's just going to stay -7x squared. And then this will become minus 12x. Okay, so that's what that would equal. Now remember, if it's exactly the same, that gives us an even function. If it's exactly opposite, so that would be negative, positive, negative, then it would be odd. But we are negative, negative, negative. So we're not exactly the same. We're not exactly opposite. So this is, in fact, a neither. All right, use limits to describe the end behavior. Okay, so we are a cubic function. So we're an odd exponent, and our leading coefficient is positive. So we're looking at the limit as x approaches negative infinity would be negative infinity. Remember, it's the same thing as a line. So that's like this. And then the limit as x approaches positive infinity would be positive infinity. All right, find all real zeros. All right, that means I'm going to factor. So I can factor out an x, factor again, and now set those equal to 0 is going to give me 0, 4, and 3. Okay, so that's what's going to go on our sign analysis. 0, 3, and 4. Those are all zeros. Nothing happens. There's no multiplicities. We're going to go negative, positive, negative, positive. So they want to know when we're greater than 0. So that's going to be from 0 to 3 and 4 to infinity. Again, it didn't say equal to, so you see no brackets. All right. Number 15, write a cubic function given the zeros. Now remember, for the first part here, we're going to do the sum and product rules. Okay, so that's this x equals 2 plus I. So sum means that I would add them together, because remember, we also have, if you've got x equals 2 plus I, you also have x equals 2 minus I. So if I add those together, 2 plus I and 2 minus I, my sum is going to be 4. And then my product, if I multiply those together, is going to be 5. And by multiply, we're doing 2 minus I times 2 plus I. That gives me 4 minus I squared, which is 4 minus negative 1, which is 5. That's where that came from. So then f of x is going to equal x squared minus the sum plus the product, and then our other root will be x minus, x plus 1, not 2, sorry. X plus 1. All right, and then they want that as a cubic function, so I am going to distribute that out. That would take me to there. All right, 16, the graph of f is shown to the right with points A, B, C, D, E, F labeled. What would the graph of f have an increasing or decreasing rate of change at point E? Okay, so point E is lying on a concave down section, so it would be decreasing because it is concave down. From A to B, increasing or decreasing? Okay, well, it is decreasing because our A rock is negative. Name all the points that will be local minimums. Remember, locals can also be absolutes. All right, what is the least possible degree of the polynomial given by the following table? All right, so this is the differences. So I'm going to have to write kind of small here. So my first differences would be 3, 4, 3, 1, and negative 1. All right, well, those aren't the same. All right, my next differences would be 1, negative 1, negative 2, negative 2. My next differences would be negative 2, negative 1, and 0. And then my next differences would be 1 and 1. So that's going to be 1, 2, 3, 4. Because the fourth differences are the same. All right. All right, so let's talk here. If I factor the top, it's going to give me x minus 2 and x plus 1. All right, so nothing cancels, so we don't have any holes. So let's talk about our asymptotes and all that first. So we know we've got an asymptote, and I'm not going in order, but we've got an asymptote at x equals 1. That's a vertical asymptote. Bottom means no horizontal. no holes. And the top is exactly one more than the bottom, so we do have a slant asymptote. And if you did the long division on that, you would end up with a slant asymptote at y equals x. All right, so if that's the situation, we only have one value with no hole, and that impacts our domain. So our domain is going to be from negative infinity up to 1 and 1 to infinity. Our x-intercept is going to be at 2 and negative 1. So that's the top. Our y-intercept would be plugging in 0 for x. So that's going to be negative 2 times 1. So that's negative 2 on top and negative 1 on bottom. So that's going to give me 0, 2. And then your end behavior, if you have a slant asymptote, remember your end behavior is the same as the behavior of the slant asymptote. So if you look at, that would be the same as y equals x, which is just your regular slanted line. So that means the limit as x approaches negative infinity of h of x gives me negative infinity. And the limit as x approaches positive infinity of h of x would give me positive infinity. So now it says graph. So what I'm going to do here is I'm going to graph what I know. I have a vertical asymptote at 1. Okay. I have zeros or x-intercept at 2 and negative 1. I have a y-intercept at 0, 2. And I'm going to kind of draw it here. I do know my slant asymptote, like I said, was y equals x, which is the line that literally just goes right through here. I know we don't draw our slant asymptotes a lot, but I want to be able to follow correctly. So really what's happening here is your graph is going to follow those asymptotes like so. And like so. So if you were to actually graph that, I think I might have graphed that. Let me see. All right, we're done with this. No, I didn't. Thought I did. Okay. All right. I mean, I know it's calculator inactive. I'm just saying you could see that on there as well. Okay. Number 19, use the binomial theorem to expand. Okay, so we're looking at the fourth row. So that's 1, 4, 6, 4, 1. Our first term is just x. Our second term is negative 3. Our exponents count down from 4. 4, 3, 2, 1, none. And then up. And remember, they should add together to give you your exponent of 4. So 4 plus 0, 3 plus 1, and so forth. All right, so if I work all this out, it's going to give me x to the fourth, negative 12x cubed, 54x squared, negative 108x, and 81. Okay. All right, so put your ball up here. I see your ball. Say hi. Say hi, everybody. Say hi, everybody. Okay. All right, get down. Get down. Okay. All right, so number 20. All right, the graph of polynomial function g of x is shown to the right. Use the graph to answer the following questions. All right, what is the degree? Okay, so let's talk about that. We've got all right, we've got a 0 here, right? At negative 2, at 1, and at 6. Okay, and at 6, we notice it sits, so that's going to give us a multiplicity of 3. So that's 1, 2, 3 is 5 total. Okay. All right, name increasing and decreasing intervals. All right, well, we are increasing, starting over here at negative infinity. Up to negative 1. And then again from 2.5 to 2.5, increasing all the way there. So we'll say infinity. Okay. All right, we are decreasing from negative 1 to 2.5. All right, where are we greater than or equal to 0? Okay, so that's where we are positive. So that starts, it does say equal, so negative 2 all the way over here to 1, both inclusive. And then from 6 to infinity, infinity is always a parenthesis. All right, where are we less than 0 but not equal? Okay, that's going to be negative infinity up to negative 2. Union 1 over to 6. All right. On what intervals would the rate of change be increasing? Okay, so when we talk about this increasing, we're talking about where are we concave up, and decreasing is where are we concave down. Okay, and remember that happens at our points of inflection, which are halfway between the mins and the maxes. Okay, so we are going to be concave up. All right, so we're looking halfway between here and here. So if I did that, I would do negative 1 plus 2.5. Okay, negative 1 plus 2.5, which is going to give me 1.5 divided by 2. So I'll find my halfway point there. So that's going to be 0.75. So that's where I'm going to be concave up from 0.75. And that's going to happen all the way over here, halfway between here, which will be 4.25. And then again from 6 on to infinity. All right, and then we are concave down from negative infinity because we start down to 0, that 0.75 point. And then from the 4.25 up to the 6. Okay, and again, those values right here, okay, those were found by doing the halfways. So literally negative 1 plus 2.5 divided by 2 is 0.75. And then 2.5 plus 6 divided by 2 is 4.25. So that's where those values came from. Okay. Halfway between mins and maxes. All right. Calculator on both of these. Okay, so I do already have these typed in to my Desmos. So let's talk about that. I messed up my camera. Messing with the dog. All right. Vehicles are tracked. Busy intersection of 24-hour period. Reported in the table below. All right. Find a quadratic model and a cubic model. Okay. So basically, when you're going to do that, all you're going to do is type in your table, and then you're going to select quadratic and you're going to select cubic. All right, so it's already typed in for me. So I don't need this. I don't need this. Okay, so this one is, yes. Okay, so I'm going to hit this, and I want to find a quadratic model. Okay, and I'll just write all this. So there it is. And I have all this written on my piece of paper. I'll write it down here in a second. All right, and then just pay attention right here to your r squared, 0.642. All right, and then we're going to go cubic. I'll write all this down as well, and then pay attention to your R squared of 0.977. Okay, so the closer R squared is to 1 is the one that you would rather choose. But you could also look at your table and see like the turning points, the times we're increasing and decreasing, things of that nature to tell this. So let me just go back here, write those big long equations in first. All right, so let's see. And then cubic. Okay, and we did decide that cubic was the better fit. And use your model to find the number of vehicles that pass through the intersection at 5 p.m. each day. So 5 p.m., if we're starting with T0 is midnight, 5 p.m. is going to be 17. Okay, so you could go back here and literally type in X equals 17. And you're looking for that intersection, which happens up here at 86.267. So we'll say 80, roughly 86. Okay. All right. And then number 22. So I'm going to go back here. All right, let me get rid of this. Let me get rid of this. All right, so now we're here. Again, I've typed everything in already. Let me turn it on. All right, find a quartic model. So we're going to click here. We're going to choose quartic. All right, now because those numbers go out so far, I am going to obviously do more than 3 decimal places. So you'll see that. Now, if you were to type this in your actual calculator, you're going to get like 2.005 e negative 5. Desmos doesn't do that as often on our equations as your regular calculator would do, but let me just go ahead and write out this model. So quartic, so we're going to say y equals 2, 3, 4. Okay. Use your model to estimate the average speed of the jet ski when the engine speed is at 2,500 RPMs. Okay, but if you look back up here, the RPMs are already in hundreds. Okay, so that is going to be X equals 25. You would just literally go here. It's hard for me to do this as much, y'all, whenever I already have things typed in, but X equals 25. And our answer is 54.321. And that is in knots. All right. And then what engine speed will produce a jet ski speed of 20 knots. So then I want to go back and I want my Y value to be 20. And I want to see where that intersects. That happens right there. Okay, so it's 14.196 roughly. Okay, so that gives me x equals 14.196, which, again, we want that. That's in hundreds. So that's 1400. So I'm going to round that to 1420 RPMs. Little wiggle room on your rounding there. You could have done 1419.6. You could have gone out one more decimal place or enough decimal places after you moved it to equal the same amount. All right. Next problem is our volume problem that we talked about. Remember, I ripped the paper in class. Okay, so again, I do have this already typed in. Let's talk about getting that value though before I get to what I typed in. Okay, so you know you've got a paper company contracted to manufacture a box with no top that's to be made by removing. All right, so we've got a rectangle. Okay, one side is 30, one side is 70. And then if you take away the x from each end, remember that would give you 30 minus 2x, 70 minus 2x, and then if we fold it up, it gives us a height of x. So that's what we're talking about, and I do already have that typed in. Let me get rid of this. Moving on up. We're getting there. All right, so here we are. Okay, and it wants to know, determine the dimension of the box that would yield a maximum volume. So we want to zoom out here, and we are looking for the max of this function. Up here somewhere. Here it is. Okay, right there. So the dimensions of the box give me an x value of 6.529 is what we're looking at. Okay, so if I do that, we know that x is going to equal 6.529. So then I would plug that in here. So 30 minus 6.529, 70 minus 2 times 6.529, 70 minus 2 times 6.529, and then 6.529. So that's going to give me, if you did those calculations, that's going to give me 16.942 inches by 56.942 inches by 6.529 inches. So those are our dimensions. Okay. All right. Let's keep rolling numbers. Letter C, what values of x will result in a volume of 5,800 cubic inches? Okay, so here we are. 5,800. We've got 3 different values of x right there. So y equals 5,800, and then you've got 3 values of x, which are 4.567, 8.627, and 36.807. All right, are there any values that you found in part C that are physically impossible? Why or why not? Okay, well, let's talk about it. We know we didn't actually ask you to find the domain here. All right, but if you have a value of x equaling 36, right here. Okay, if I plug in 36 right here, 30 minus 2 times 36 is going to give me a negative value. So yes, 36.807 is not part of the domain. Since it would result in a negative length. Okay. All right. Number 24. All right, so obviously we are going to rational function. We are going to factor So x plus 5, x minus 5 on the top, x minus 2, x plus 3 on the bottom. All right, so that would give us, on our sign analysis, -5, +5, -3, and +2. So -5, -3, +2, and +5. 2 and -3 are our asymptotes, and 5s are our zeros. All right. So when you are looking at this, this is the issue right here. Okay, so you've got -r of 2x. So if I just look right here where p of x is greater than 0, greater than or equal to 0. Okay, so remember that if this negative out front here reflects this over the x-axis. Okay, so the whole thing's going to flip. All right, so we're looking for p of x to be greater than or equal to 0. So that's going to be where r of x is less than or equal to 0. Okay, so let's talk about right now where r of x is less than or equal to 0. So that's going to happen. So our r of x values are going to be from -5 to -3. Sorry, I didn't write my sign analysis. It should be positive, negative, positive, negative, positive. My bad. Okay, so right here and right here is where r of x is less than 0. Okay, union 2 to 5. All right, so now we have to transpose those into our function up here. Okay, so inside means we are only changing the x values. Okay, those are horizontal movements. So that messes with our x values. So the 2 is going to that x. Okay, so we need to say that 2x would equal -5 and 2x would equal -3. All right, so that's going to give me x values of -5 over 2 and -3 over 2. Right, so -5 over 2 to -3 over 2. All right, then we need, so that's this one and this one. Then we need 2x to equal 2 and 2x to equal 5. So then it goes 1 and 5/2. Okay, and there you are. All right, so once you figured out what you had, the negative reflected it, so we had to switch intervals. We wanted the negatives instead of the positives, and then you apply your transformations. All right, number 25. Again, calculator problem, so I'm going to go right back over here. Done with this one. Done with this one. All right, turn this one on. And here we are. Let's go to home so we can see it. All right. So looking here, it says how many deer were present initially. So that is just your y-intercept. If I click on the line, the y-intercept is 40. Find the number of deer in 15 years. Okay, so literally 15 years is just P of 15. So by putting it in this way, I can just type in P of 15 and there that is. All right, limit notation in behavior. So we can see as we're going towards negative infinity, we're approaching a certain value, and positive infinity, we're approaching a certain value. Okay, and that value is our horizontal asymptote, right, which will be 640 divided by 0.8. All right, so what we've got here, okay, let me fill in all that information that we just talked about. All right, so what we've got here is we know our initial, our P of 0 was 40 deer. We know that our P of 15, okay, you could literally write that out if you wanted to, the 800 plus 640 times 15 over 20 plus 0.8 times 15. But again, we just did that. So that gave us 325 deer. All right, we know our limit as x approached negative infinity was 800, and our limit as x approached positive infinity was also 800. So what does this mean? Okay, so according to the model was the largest possible deer population. So we know we were approaching 800, we can never equal 800. All right, so it's going to be 799. Okay, the value we know of the horizontal asymptote is y equals 800. So the number of deer will approach but never reach 800. All right. Okay, so that is all of that part of the review. Okay, there is some vocab, just in general, just reminding you. A lot of the vocab is more of, I didn't even take the picture of the back. I'll take a picture of the back for y'all. So I'm gonna slide that under here just real quick and let you, if you want to look at the video to do this, just hit pause and fill these in. The front page is on Canvas. I don't think I put the second page on Canvas, so I'm gonna flip that over. All right, again, just pause it, fill in what you need to. Okay, here's the top and the bottom. All right, and I'll try to get that uploaded. Okay, so again, out of school tomorrow, right now, 2026. I don't know how many times I'll use this video, so I don't want to say that, and then people think we're out of school. All right, so February 2nd, 2026, you're out of school. Remote, you're supposed to be working on this. And then again, if you go into your Canvas, you will find the other review that I had. Oh, where I put that one. And I will work through that one most likely as well. In a video tomorrow. All right. Y'all stay safe, stay warm, and I will see you as soon as we return back to school.